So in this video, we're continuing on this idea of assessing goodness of fit. And now we're going to focus on interpretation of various tests of goodness of fit. But we're going to begin with a code. And I want to start kind of as a review. Let's think about this thing fit. So what does this thing fit here? It's the sum of these guys here. And where did these guys come from? These guys are a reflection of the difference between the observed values and the model values. So these are the model values, mu I. These are the pop sizes, the observed values. And what we're looking at here is taking the difference, taking these differences between the observed and modeled values, and then we're going to take these differences, we're going to square them. Take those differences, and then we're going to square them. And here, what we're doing is, if you think about the fact that everything here is based on a loop over 16 years, we're going to exit that loop, and then we're going to sum those square deviations over the 16 years. So now let's look at fit new. And it's going to arise, the process here is going to be somewhat similar. So fit new is based on this thing here, and this thing here is based on that. And so what we've done is we've generated a new value, y new I. And that's really the key. And this is kind of the power of JAGs, is that what we've got is this line here. So remember, at each iteration, we get a new value of alpha, beta, and tau. And given that we've got these new values of alpha, beta, and tau, at each iteration and for each year, we can generate a new value. We can generate a new value by taking a single observation from a normal distribution. This has as its mean mu I, which is going to be alpha plus beta times year I, and precision tau. So we're able to generate these new values of population size. So we've got our new values of population size that we can compare with the modeled values. So now we're focusing on those dark squares. So we take these differences, we square them. So we take these differences and square them, and then we exit the loop with the 16 years and sum up all those values, all those square deviations over the 16 years. So that gives us, at this point, fit and fit new. And the overarching approach to our goodness of fit test is stated right here. So we've got these values of fit new, and we got these values of fit, and the idea is that if we've got a well-fit model, then about half the time, the discrepancy between, in this case, the newly generated and the modeled, in this case, the observed and the model, those sum square deviations should be about the same if our model is well fit. So one way to see whether or not half the observations have fit new greater than fit, the other half they don't, is to do a simple plot. So what we have is fit new on this axis, fit on this axis, and it does in fact appear to be the case that about half the time fit new is greater than this line, half the time is less, and this is a line of equality that says that the intercept is equal to 0 and the slope is equal to 1. Now, this sharp edge here isn't worth worrying about. If you are concerned about it, it's explained in the notes. So that's one goodness of fit test. The next goodness of fit test also uses this principle, comparing fit, new, and fit. But now what we're going to do is use the step function. And so if you recall how that's going to work, is that if fit new is greater than fit, then the step function will return a 1. In contrast, if fit new is less than fit, then the step function will return a 0. So we've got all these iterations. And in each one of these iterations, we calculate our BP value as either being a 1 or a 0, and we monitor it. And at the end, here's what we see. 3 chains, 9,000 iterations per chain. We've got 27,000 values that are either going to be a 0 or a 1. And on average, we get a value of 0.5511, which is a pretty good indicator, if this is our criterion for goodness of fit, that about half the time fit new is bigger than fit, about half the time it isn't. And now, our last index of goodness of fit is going to come from here. And what we're going to do is we're going to loop over the 16 years. So in each one of those 16 years, what we're going to do is compare this newly generated value y new I with pop size I. So if we come back to our diagram here, what we're comparing is y new I with pop size. So we can think about those as being, let's see, there's a difference there, there's a difference there, there's a difference there, there's a difference there, there. So we're looking at is the difference between y new I and pop size. And again, what we're going to use is our step function. So if y new I is greater than pop size I, then we get a 1. Otherwise, we're going to get a 0. So what we're going to have are, for each year, we're going to have a value of check. So we're going to have essentially 27,000 values, 1 per year, of the value of check. And so we can look at that down here. So here are our values of check for the different years. And so again, similar to what we saw before, if we've got a really well-fit model, then half the time y new I should be greater than pop size, the other half the time it should be less. And so if you think about, for each year, you've got all these 1s and 0s, you're going to have essentially 27,000 1s and 0s for each year, because you got 27,000 iterations. Well, not surprisingly, the lower credible interval is always going to be 0, and the upper credible interval is always going to be 1. But what really is important is the mean, the average of all those 1s and 0s separately by the year. Again, a well-fitting model would give you a value of check around 0.50. And most of these aren't bad. What Carey points out, that there's 2 that, aren't really nasty, but you might want to think about, is that you've got check 8 with 0.908, and then you've got check 14 with about 0.054. So in this case, about 91% of the time, in this case, 5% of the time, it follows that y new I was greater than pop size I. So just kind of some summary thoughts. I mean, frankly, I find these goodness of fit tests, as shown here, a little bit confusing. So I'm not totally comfortable with it. The other thing that makes me a little bit uncomfortable with it is I generated some data from models that I made so that they wouldn't fit very well, and I wasn't able to detect the problem with these goodness of fit tests. So that's kind of worrisome. I wouldn't get too bent out of shape about the details. I think one of the big advantages of going over this goodness of fit stuff is to realize that, ultimately it is going to be an issue that you're going to have to address. So you're going to have to think about goodness of fit. And the other reasons for going over this goodness of fit test is the idea it gives us once more an opportunity to understand how this JAGS package actually works.